Okay, hi everyone. Thanks for coming. So we have two talks today, both from the US CMS and OPS programs, CMS and Atlas OPS programs, and actually these are both Atlas, I think, on sort of research focused on or looking towards Run 4 HL-LHC work. So we'll go ahead and get started. So the first talk is Rui about hyperparameter optimization service at Atlas. So go ahead and get started. We'll interrupt you with questions and then more at the end.
Okay. Yeah. Good morning or good afternoon, everyone. So my name is Ray from the University of Wisconsin-Madison, supported by US Atlas. So the work is about the hyperparameter optimization service at Atlas. So today I'm going to go through briefly the following items. So first I will introduce the project, also briefly introduce the hyperparameter optimization. Secondly, I go through the IDDS service that the hyperparameter optimization service rely on. And I will talk about this procedure, the workflow, and the ingredients of this service, basically. And one interesting variation of this workflow, the so-called segmented HPO workflow. And then I will talk about using heterogeneous resources to do the hyperparameter optimization or machine learning. And finally, I will show some visualization support in this service. First, the introduction. So the goal of the project is to provide a HPO service to Atlas users. This, from the beginning, the design is to have minimum user code adaptation. So if user already have a package that can run the machine learning, they should have a minimum change in order to use this service. We also would like to support advanced search algorithms, not only the traditional grid or random search, but also some Bayesian or other types of searching algorithms. And since Atlas already have the production and the distributed system, so-called Panda, we would like to reuse the system instead of reinventing all the things from the scratch. We also would like to support visualization of the training. If you have a lot of hyperparameters, you want to compare different parameters, how the results look like. So it will be very important to have a visualization. So for hyperparameter optimization, there are two patterns that you can use. So one of the popular one is the single function call pattern. So this is basically you say, I want to do a hyperparameter optimization in one function call, and under the library will do the computing resource management. It will distribute different points to different nodes, and then finally collect the final results, the best result. However, this is not suitable since Atlas has its own resource management. We have the grid sites, and we have Panda to schedule different jobs. So it's not very suitable to just do one call, and this one call will instead of doing the resource management. Luckily, we have another pattern, this so-called ask and tell. So this is basically to separate these two steps or decouple the optimization and the sampling from the training in space-time. So what it means is you have a search space. So you purely do a point search in the search space. And then given this point, you evaluate the result of that point and tell me back the performance. And then based on the performance, according to some optimization algorithm, I can do another point search. So this is also easy to implement. And some libraries also support this pattern. So we would like to go this way. So I will talk briefly about this IDDS service. This is also a joint project with IRIS-HEP. So this is designed to intelligently transform and deliver needed data to workflows. So this is not designed for hyperparameter in the beginning. However, the idea of IDDS is that the jobs with successive tasks can start as soon as possible. So you don't have to wait for the previous task to finish. Some of the successive jobs can already start it. So there's a graph showing the data transformation in the IDDS. But basically, the IDDS is like a controller of which job should start and when. So there are many applications that has this type of demand. For example, data carousel. So in this case, jobs starts when the input is ready. You don't have to wait for all the data set to be transferred. You can already start it once part of the data is transferred. Another use case is like if you want a chain of tasks, you define the tasks as a chain, a logic chain. So the successive tasks, jobs can start if the previous jobs finish. So you don't have to wait for the other jobs to finish in this chained task. There is another type of chain task, this active learning. The difference between this like DOMA and active learning is in active learning, you can do some decision between the previous task and the current task. While in DOMA, you don't have to do the decision making. So this different, although they looks quite different, but the idea is you have this sequential tasks and you want to do in a finer grained level. So hyperparameter optimization is also suitable for this kind of idea. So we want to search for a lot of points, evaluate a lot of points in the search space. Well, we also want to know what's the result from the previous point. And based on that, we predict the next point. So there is some decision making involved between different points, but also the points are can be sequential or can be parallel. So this is a good candidate to use IDDS as well. So on slide 6, I'm showing the workflow of the hyperparameter optimization service at Atlas. So from the bottom, as a user, if you want to do a hyperparameter optimization, you first have to define what is your search space, like which hyperparameter you want to optimize, the learning rate, the batch size, and so on. This can be different for each application. And of course, the training code, which can be just some simple script or some package or some repository, many people may prefer. So as long as you have these two things, you just submit a task to Atlas Jedi, which is the job scheduler. And Jedi will make a request to IDDS. So IDDS will run in a so-called steering component, which is using a Docker image, a Docker container to do that job. But essentially, this steering will just give you some points in the beginning. So the point will passed from IDDS to Jedi. So Jedi will take this point and submit job with this point to Panda. So the Panda will run this job at any site at Atlas. And in that site, the site will run an evaluation container, which contains the training job. Basically, the user have to put this training code into the evaluation container, and the evaluation container will know the point, and it will run the training. And afterwards, there will be a metric, for example, the loss from the whole training. Then the evaluation container will report the loss and back to IDDS. So IDDS knows the metric of this point, and then the optimization can update its knowledge and predict the next point. And then this can be a loop until like the maximum points is achieved from the user definition. So there are several essential components in this workflow, and we use two containers to fulfill the whole loop. One thing is the steering container. So this is running on IDDS server. So this is basically to generate the next hyperparameter points with whatever method the user prefer. So in this container, we support a wide range of hyperparameter optimization methods. And another container is the evaluation container. So this is a real training happening inside this container. This is also called the payload. So in the container, user can put their training script or their Git repository to the container or as a submodule or whatever. As long as this container is launched, it knows what the command to run the training, then it can evaluate the final loss. In addition, we also support the checkpointing in this workflow. So during the training, the checkpoints is periodically updated, uploaded to Atlas Grid. So the checkpoint is basically to solve the problem that some sites may fail in the middle of the training or the wartime is reached. So the job will be like crash. So Atlas will retry, Grid will retry the job automatically if it's not finished successfully. So during the retrying, it will check the checkpoint and download the checkpoint if there is any. So the training can resume if it finds a checkpoint. So on slide 8, I'm a little bit switching from the usual HPO workflow to talk you about the so-called segmented workflow. So why do we need this thing? Some machine learning payloads have similar architectural models targeting different physics regions or objects. So essentially they can be defined in a same manner, but maybe it's just some minor parameters that are different because they would like to target different physics region. So this in principle is just many models, so you can submit many tasks into the grid. But once this number is large, bookkeeping is very difficult. For example, a real Atlas example, this so-called fast calogan. So this is to generate the calorimeter image. And this is a generative model as seen from the name. But you want to have a different generator for different particles like the photon or electron or pion, and maybe also different eta slices. So in the end, currently there are 300 GANs with 3 types of particles and 100 different eta slices. So this means if you want to train for the whole Atlas detector, you would need 300 individual GANs. So now this can be done with segmented HPO, and you can do it in just one task. So the idea of the segmented HPO is the differences from the normal HPO is so in the normal HPO, one machine learning model is using the same data set to do the training. So it's just one model. While the segmented HPO is you have like a template of the model, and the model can be configured with different parameter, for example. Then each different model targeting different parts of the whole picture. So this workflow, this segmented HPO workflow is like additional to the normal or to the Euro workflow. So what I'm showing here is just I highlighted the difference between this workflow and the previous workflow. So for example, from the beginning, from the bottom, as a user, we still need to define the two previous one, but in addition, we need to define the segment. Like in the GAN, you have to define which eta slice, which particle you want to train. So you will have 300 segments. Then again, you submit the whole task, and the grid will internally convert your segment name to some model ID. So this model ID is hidden from the user. User only care about the segment name, but inside the whole workflow, we actually dealing with some integer ID. So basically the logic is very simple. You just carry the model ID along in every step. And in the evaluation container, again, this will convert to the segment name. So the user who prepared the evaluation container again sees its segment name appeared there. So when you do the training, you know which segment you are targeting. So this is also implemented currently. And we support both the Euro one and the segmented one. So if you don't have any segmented task, you don't need to do to change anything. But if you have a segmented task, then you just add the segment definition. So this is very simple. Just whether you provide an argument or not provide an argument. So also to reduce the load of the sites, we support separating the input data set for each segment. Because if the number of segments are huge, the total in training data might be much bigger than the real training data each segment needs. So in that case, you would prefer only download the necessary training data, not the whole training data. So here I demonstrate that one of the segment only downloaded the training data it needs, not all the training data. So we did this test with now with up to 15 GANs to test the scalability, which is three particle types and 5 eta slices. And also for this particular example, so since it's a generative model, it requires a lot of training epochs. So ideally it wants 1 million epochs. And you don't specify, you don't basically stop the training. You want to run over all the 1 million, and afterwards you do a dedicated offline analysis to find out which epoch or which parameter is the best. But for the test purpose, I only run like 10K epochs on the BNL GPU site to demonstrate that everything works. So on slide 11, so after integrating all this into the Atlas grid, we would like to incorporate other GPU resources for the machine learning or hyperparameter optimization. So here, the example is the Summit at Oak Ridge. Because Summit has a lot of nodes, and each node has multiple GPUs, so six GPUs. So this is a wonderful workstation for machine learning or hyperparameter optimization. However, there are some challenges. So for HPC, they prefer to have short running time, but with a very large number of nodes. So I will come back to this later. And also for HPC, according to our previous experiences, so the workflows are not always available, or some are not optimal. So what we did is to try to integrate Summit to Atlas Grid, which is basically the first step to do. So for HPC environment, Harvester in Atlas is the key component. So Harvester do the communication thing between Atlas Grid and the HPC. So what we have to do here is basically to connect the components. So the Panda IDDS and the image, the Docker image, to Harvester. So basically to build up those three rows. So yeah, so we had many challenges on this. So the following ones are like the most noticeable ones. So first of all, Summit is IBM PowerPC IBM PowerPC architecture. So it's a non-x86 architecture. So this means you have a very different environment on the machine. And the Docker image is indeed architecture dependent. So you need to prepare a PPC Docker image specifically for Summit, which is fine for the steering container because we provide them centrally. But for the evaluation container, it's not so easy to teach users how to do it. Another challenge is it has a very short wartime, which is okay if we have the checkpointing, but still it will be like most of machine learning applications will run days. So like 2 hours every time is not optimal. The most striking challenge is the network connectivity of the worker nodes. So there is no outer bound or inbound connectivity. That means during the training, you can't connect to the internet, so first it requires all the components to be downloaded in advance, and also some training jobs they may sometimes require something, so it's not very fun there. So we also considered the commercial cloud as another type of resources. Also, this is basically suitable for the so-called distributed training, which requires multiple GPUs or multiple nodes. Because the GPUs on grid are mostly for single GPU training. Well, Summit do have a lot of GPU, but for the user, it's not a best place. So we are currently doing R&D on this commercial clouds. So we do this because we don't want to, we just want to do some experiments and see how it will work. And also for the distributed training, even though we are not, we don't have many applications at the moment, but since this is a very popular idea outside of HEP, we anticipate in one day, if we have a very large data set, the distributed training will also be needed. So currently, we are experimenting HelloVolt. So we created an evaluation container with this HelloVolt application and doing some multi-GPU, like plan to do some multi-GPU tests. But we also open to support other distributed solutions. So on slide 15, I probably should be quicker. So this is a simplified version of the integration integration map on Amazon Cloud. So here we again need the harvester to like submit the job on behalf. So the idea is the harvester will submit a job to the Kubernetes head pod, and the head pod will depend on how many GPUs require or how many GPU it can auto scale. The head pod will create the worker pods, and once the training is done, the head pod will report the loss to IDS. And then there can be a loop continuing. So I think my last topic is about the visualization support. So a visualization tool, MLflow, is by default turned on in the evaluation container. So this is useful for offline visualization as it's part of the output. So users can just download the output and run a MLflow in their own laptop to check the results. But we also have an alpha version of the tool integrated into Panda monitoring system. So this system will fetch the output from Panda, from Lucio, and spin up a MLflow container. So it's similar to your own laptop, but you don't need to have your own laptop or install this thing by yourself or downloading the output. This is also extendable to other visualization tools. There are many visualization tools in the market right now. So as long as the output from the evaluation container match the format of that tool, or we can provide a additional conversion step from that tool to MLflow, for example, then users can visualize the results as same as the MLflow one. Okay, so today I talked about the project of myself, which is to provide an ML-HPO service at Atlas. So this is to fulfill the demand that is anticipated from the machine learning topic of physics, in particular in HL-LHC when the data set becomes large. So it's an Atlas directed work, but could be used by other experiments as well. The HPO workflow is developed and tested. So we adopted the ask and tell pattern, and so they are separated, so we can like install them into the Atlas Panda system. And in both steps, Docker image is used to preserve rapidly changing machine learning libraries. We did some tests with several use cases in Atlas, and we summarized what a user needs to change if they already have a mature machine learning training package. I also talked about some special scenarios. One scenario is the distributed learning. So there we tried to do something on the HPC or Summit, but we faced some challenges. And we are also working on the commercial cloud. Right now it's the Amazon one, but it's we probably can extend it to other companies. Another scenario is a segmented HPO. So this is implemented and tested. This will be a convenient work framework to train hundreds of models in one go, and it will be useful if Atlas migrate to the machine learning-based simulation. In addition, visualization is also supported, both in the evaluation container that you can download, or via the Panda monitoring system. So there we also have many other ideas that can be implemented. Yeah, that's all for my talk.
Great, thank you. Very nice. Who has questions? Gordon. Or maybe that's a chat and not a hand. Gordon's going to write it. Anyone have a question while Gordon is writing his? If not, I had one. It wasn't really I think it's not really the point of your nice tool, but you talked about your experience on Summit, that the architecture was one of the challenges you had. I was wondering if you could say more about that, because this is a case where I would have expected most of those things where you're packaging machine learning tools into a Docker container, which it sort of sounds like the perfect way to hide architecture difficulties from users.
Yeah, so a direct response to that is the PowerPC architecture requires a PowerPC container, which is not very, so Summit use Singularity, not Docker. So we have to find a way to use both Singularity and PowerPC, which is like double challenged. So this is one thing. Also, to keep in mind, we have to allow users to do the thing we are practicing. So if we can do something, it doesn't mean the user can do it efficiently and conveniently without any additional resources. So this, we try to find a solution, for example, to grab the native libraries from Summit, plus some additional libraries we have, and plus something in the Docker or image already, to make a mixture of all the available libraries to try to support various users. But still, the key thing is user seems to not have the freedom to put anything they want in the container, in the PowerPC plus Singularity container. So that is most,
yeah.
Yeah.
Thank you. Okay, let me read Gordon's question. So yes, when running hyperparameter training, randomness is part of running. So even when you find the best set of hyperparameters, you want to keep that particular run, sort of like checkpointing each single run. He's wondering how that is handled.
Okay, so yeah, this is two parts. One is the randomness. So for the randomness, it's the nature of the hyperparameter optimization. So as long as you evaluate different points from a different initial random position, you might get a confusing answer if you do several times. So this is something I think it's a general machine learning question. So I think from myself, one suggestion is to do several times for each point and take an ensemble of the training. But this, of course, will double or triple your overall training time. The second one is the checkpointing for each particular run. So this can be done from the user side. So everything user can decide whether they want to save the final model or they want to save the model periodically as the output. So it's like the standard Atlas job, whatever output you saved, then you can download it afterwards from the grid. I think he has a follow-up. So
I think he's saying it's very cool.
Yeah, he also has a follow-up for the.
Okay.
Yeah. Yeah. No, it's not supported by this infrastructure. So the question is whether the several training per point is supported. No, it's not. What you can do is for the evaluation container, you do several times by yourself. So you receive every point, you can do several times, and then you average the loss and then report to IDDS. So all this part can be done by user. So the user can define whatever they can do in the evaluation container.
Okay, thanks. Anyone else with questions before we switch topics? Don't see any. Okay, thanks again. I think that's really interesting. Okay, so then the second talk is Vincent about, I guess, cross-platform random number generation with SYCL.
So this is some work that we started back in December, part of ATLAS and the HEP CCE project, which we're trying to evaluate different portability solutions. And this was one that we needed for a number of reasons, which I'll discuss. So we ended up basing a paper. I worked with, I collaborated with Mehdi from CodePlay out of Edinburgh, UK, who's also, CodePlay is also partnering with NERSC on getting SYCL and CodePlay Intel software running on NVIDIA hardware, which will be hosted at NERSC with Perlmutter. So that's where this information is coming from. So the motivation is, yeah, we have a bunch of new machines coming out in the future. Some already are available, such as Cori, but we have a number of others that aren't just NVIDIA based. So they're going to be in Intel, AMD, all these different heterogeneous systems. And what this really means is that to run your software, you have to write it a multiple number of times in order to run on any one of these given machines. So there are some what we call performance portability solutions or APIs or platforms that can help to address this, such as Cocos and Raja. And then the many variants of SYCL, which I have a little chart at the bottom that shows the different releases or flavors that are available for SYCL and their compilers. And the question is, there are a whole bunch of machines, but what will we really have access to? And I think that ultimately, I don't know that answer, but we need to be able to use. I think the DOE has made it clear that we need to be able to use these heterogeneous resources in order to have access to these powerful machines. So how do we write performant code once and be able to utilize all these different types of hardware and platforms? Specific to this talk is random number generation. So in ATLAS and HEP in general, there are a number of different things that are used for that use random number generation, basically from all the way from event generation to analysis. So event generation, parton showers. In simulation, we have to sample energies and secondary productions. What comes to mind is fast calosim, of course. I'm a bit biased. That's an ATLAS fast calo simulation software, as well as digitization for detector readout emulation and also sampling pileup distributions. And then even at the analysis level, TMVA, and with the rise and ubiquity of machine learning now, random numbers are used everywhere. But this really started with the need to look at fast calosim because we wanted to evaluate SYCL's CUDA backend and compare that with with the Intel backend. So this brings us to performance portability, and I link here the paper on the archive from Pennycook and others. And you can see that there are a number of different definitions for performance portability, almost as many as there are platforms that we'll have to target. But the one that they propose is that it's a measure of an application performance efficiency for a given problem that can be executed correctly on all platforms in a given set. So more formally, they have this harmonic mean representation where you have this fancy P as being your performance metric, little p being the problem that you want to solve, A, application, big H, a set of platforms that you're trying to target, and then the E sub I, A of P is your efficiency, which can be, say, for example, architectural. So how efficient does your software run on a range of different architectures, and so forth. So you can think of this as like kind of like a fancy or a way to visualize or formally describe a roofline model, where you would have, you know, a non-zero value if your software runs on every platform in your set H, or zero otherwise. So for example, CUDA would get a 0 in this right off the bat, because you can't run CUDA on anything but NVIDIA hardware. Raja, Cocos, SYCL, they would have non-zero values as long as you had H is not including any platforms that weren't supported. But that's the aim of these portability layers, is that they should, or they aim to be able to run on all hardware. So I show on the right a plot from some of the studies that we've done so far, our Atlas FastCalloSim on GPUs, where you can see the different backends at the bottom and their runtimes on the y-axis. And really what we're trying to do here with this in adding cuRAN backend to 1MKL is that we want to see how SYCL performs on CUDA backends relative to, say, Cocos or HIP or what have you. So a little bit about SYCL, 1MKL, and cuRAN. So SYCL, I think most people know by now, is an open source open standard single source, which means that you could run, you can program host and device code on the same file. It's C++ based for parallel programming on heterogeneous platforms. And this is basically a specification that's put out by the Kronos group, which includes people from Xilinx, Intel, CodePlay, as well as from academia and research labs. 1MKL is Intel's SYCL-based open source interface library, which has things such as BLAS and random number generation functionalities for the various backends, such as x86, Intel GPUs, and now NVIDIA GPUs. And cuRAN, of course, is NVIDIA's closed source, but highly optimized pseudo and quasi-random number generation library, which comes in 2 flavors, one that targets a host, which you can produce random numbers entirely on your host or your CPU, or you can offload the actual random number generation to a device from the host. And alternatively, with the device API, you can do everything entirely on the device. So you don't need any unnecessary data transfers should you want to share those numbers or data. So on the right here is just a plot of how the 1MKL SYCL-based interface actually corresponds to the different backends. So we have a RNG, random number generation, and a BLAS backend. And then these tie into the different vendor optimized libraries such as Netlib, cuBLAS, and Intel MKL. And at the very bottom, we see the different hardware platforms, which of course include GPUs and CPUs alike. So some technical aspects and limitations on our implementation. So I have this table on the top left showing the different headings, 1MKL, cuRAN, and then our 1MKL cuRAN backend. So basically what you need for this right off the bat is if you want to target CUDA devices, you have to have a compiler that supports parallel thread execution or PTX. In 1MKL, we have this, and in SYCL more generally, we have what are called buffers and USM APIs. So buffers are kind of like the original native SYCL way to handle memory, and it takes care of a lot of the under the hood work for you, whereas USM is more akin to people who've done C++ programming and CUDA programming in the past. It's basically working with raw pointers and managing the memory yourself. So in 1MKL cuRAN, the second row, last column, we integrate both buffer and USM APIs. And as far as we know, this is the first demonstration or performance measure of the USM API for something like this. 1MKL has inverse cumulative distribution function methods for pseudorandom generators. In cuRAND, we only have this for quasi-random generators. So as a result, we have not or could not at this point implement this into our new backend. In 1MKL, you have a distribution that you can give it, say Gaussian or uniform, and you can specify the ranges on which you want the output sequence of random numbers to lot or fall within. In cuRAND, you have fixed sequences, and basically these are always unsigned integers or double or float. And if they're double or float, say a normal distribution, they're always generated between 0 inclusive and 1 exclusive. So what that means is that for us to integrate the same functionality in 1MKL, we had to add an additional number of kernels that can do this, this range transformation. In 1MKL, there's copy construction as well as seed initializer lists for constructing the generators. Neither of these are available in cuRAND, and as a result, we don't implement it. It was out of the scope of our work here. On the right gives you the idea of what the difference between the buffer approach and the USM approach. Again, the buffers, SYCL buffers just really take care of the data dependencies for you. That's what this flowchart is showing you, from the top application scope to the middle row command group scope, and then finally at the bottom the kernel scope. Whereas on the other hand, USM, you have to take care of all the data dependencies by yourself, because the SYCL runtime DAG does not handle raw pointers as you would expect. You know, buffers are kind of like a glorified pointer approach. And then finally at the bottom, I have two different, just to show the similarities between the different generators in 1MKL on the left and cuRAND on the right. You can see that basically their function signatures are relatively the same, very straightforward. And one, on the other hand, on the left, 1MKL takes this constant uniform or distribution type, whereas on the other hand, with cuRAND, you give it an explicit generator type, and you call a specific function, fixed function, depending on what type of distribution you want to sample from. This is not the right slide. What happened here? Okay, so the implementation details of cuRAND and 1MKL. So in 1MKL, we have each generator class comprises 3 constructors and 36 different types of generate functions, 18 of which are for the buffer API and 18 are for the USM API. Due to the limitations I already spoke about, we can only implement 20 of the generate functions. The other ones we relied on ICDF methods. And what's nice is that we have identical signatures for both x86 and GPUs to facilitate this pointer to implementation. So basically it's transparent if you want to call any of these functions for any backend in your application. And on the right, we just show a little code snippet of an example. So at the top is where we do our construction or creation of our generator. We set our seed. And then here we have one example of a generate function where you have the command group scope highlighted in green and then the kernel scope in orange. Now, what's nice in the kernel scope is that we leverage SYCL's interoperability, which I think, you know, CodePlay actually introduced this into Intel's LLVM or their compiler. But basically, this allows you to call from the host any third-party library that you have access to. So any interfaces you have, you can see we take the cuRAND call, and which is just a definition, and we call a cuRAND generate uniform with some parameters, and then we do a device synchronization at the end. And depending on what we're generating exactly, we can do this range transformation kernel at the bottom, which just adjusts the range of the random numbers that were generated. So for benchmarks of performance portability, we looked at different 3 different platforms. One was the Intel CPU, one integrated Intel GPU, and an NVIDIA Quadro RTX 5000. And you can see the specifications here of the different hardware. Basically, as you go down the list, you become slightly more powerful, but you also lose, you know, clock frequencies because you know your CPUs generally have much higher clocks or much faster clocks than your GPUs, but at the you also lose compute units or cores. So our measures are based on basically 2 metrics. One is the total execution time, TET, and then the kernel only execution time, KET. And the difference really is that the TET includes memory allocations, the data transfers, generation, post-processing, and synchronization, where on the other hand, the KET timing only includes generation and post-processing. So these are our results that we have included in our paper. I apologize if it's kind of hard to see if it's small. So I will just zoom in on the next slide to make it larger. This is the results for a Phylox-based generator with Gaussian distributed 64 or FP64, so 64-bit floating point numbers. And the different colors here correspond to the different platforms. So in the fuchsia is the CPU, in the light purple is the native CUDA, and in the dark purple is our 1MKL Kuran backend, and then green is the integrated GPU. And one thing to notice is that first, you don't always want to, or you don't always need to offload calculations to a GPU, as we demonstrate, as we show here. I think is obvious to everybody, but this is a nice illustration of that. Is that for small batch sizes, so a small number of random numbers that are generated, your CPU outperforms, and you likely already have that code. So you don't really need to go in and rewrite your code to target a bunch of different platforms if you don't have sufficient workloads to offload to GPUs. Next is the purple. So you can see that there's this constant overhead between the light purple and the dark purple. It's denoted by this arrow here. And this is basically a constant overhead that's introduced by the SYCL runtime. In CUDA, you only have a single context, and this context is shared among all devices, so you don't have to manage a bunch of these. Whereas in SYCL, you have a different context for each queue, or at least you should. And this means that whenever you're calling a third-party library, or you're calling some function from the CUDA API, you have to find the correct context among all the contexts that are currently available, and you have to record and load that every time. So that's where this constant overhead comes from. If we look instead over at the right, you still see this overhead, which is in the kernel execution time plot, but for significantly large workloads, these two lines converge. And this just goes to show that SYCL can run your native, or SYCL can execute CUDA code using SYCL interoperability with basically no hit or no degradation if you have, again, sufficient work to be done. Because this little overhead that pertains to the context switching and so forth is really negligible once you're really using the full power or near full power of your GPU. So that was very nice. And then we drive this point home by looking at some data that we got from Nsight Compute. So this is CUDA, NVIDIA's kind of GPU profiling tool. It's very powerful, very nice. vTune, I think, or Intel's vTune is kind of getting there, but it's not quite there yet. Before I go into the details of the plot, I should also say that whether you compiled your code with a SYCL compiler with the PTX backend for CUDA devices, or you use NVCC directly, you can still profile both with NVIDIA tools, because you're actually, in this case, you're looking at specifically the kernels that are launched, which come from the CUDA library or API. So you can still, even though you compile your code with a SYCL compiler and you've written your code in SYCL, you can still profile that code with NVIDIA tools, which is really cool. So just to get into the details a little bit of this plot, so this is a breakdown of each of the 3 kernels that are launched in our test applications. The first one is just the random generation seeding, which is basically the constant line, dot dash line at around between 10 to the 4 and 10 to the negative 3. The dash line that lies just below it and then slowly rises basically linearly is the generation of the random numbers itself. And the dotted lines are the range transformation functions, which we've implemented ourselves. So this is not from the CUDA library or API. This is something that we've implemented on our own. And then finally, the solid lines are the combination of each of those. So you're adding each of those 3 kernels, summing them, and then plotting. And what you see here is basically in all cases, these lines are essentially lying on top of each other. And with the exception that higher workloads, we have this slight separation beyond a batch size of 10 to the 5. which admittedly I don't quite understand yet, but I think we can safely say like we're getting really, really solid, nearly native performance with our backend. And finally, just to conclude and talk about a little bit of future work. So what we've done and what we've written in our paper is that we've integrated a vendor optimized Kuran library as a new backend to the open source Intel 1MKL Intel 1MKL library, sorry. We leverage SYCL interoperability to really coordinate and orchestrate the resource allocation and to perform the native CUDA library calls. And basically, I think we've demonstrated that it's feasible. You can have a cross-platform portability of SYCL for this specific application and others. This is just one example, demonstrating that you can execute equivalent native Kuran kernels on Intel and NVIDIA hardware in a single language. You don't have to write in SYCL for Intel. You don't have to write in CUDA for CUDA. You can write it in SYCL, and you can run on both types of hardware. That means you can take advantage of multiple heterogeneous systems and with a minimal amount of work. So for looking forward, we want to use this test bed of 1MKL Kuran for further studies. So like I said, this kind of all stemmed from not having a random number generation tool or engine available in SYCL to run on CUDA devices, but now we have. So this is the next step would be to take a look at how this actually works in our FastCalloSim code. We also noticed that because what we've observed is compute bound, then we can do some performance optimizations that can significantly affect the size of the input. So for example, we can use different hardware. You noticed before for smaller batch sizes, the CPU is your best bet. It runs quickest. And then beyond that, you have a number of different platforms that you can choose from to really get the most out of your machine. And also there's a number of different CUDA libraries, of course, that people know about, QFFT, which is a big one, QSparse and so forth, that can also be added to 1MKL to really have this performance portable library for math kernel executions. And lastly, just to show this an updated plot of the SYCL ecosystem, I just want to show DPC++ and Intel 1 API was really the PTX backend was introduced by CodePlay, but now Atlas is in high energy physics has somehow stepped in and helped out with this effort. So I think that's really something that we should be proud of. And then also, we have this matrix here of the different types of platforms and the codes that can run them. And again, we can really, kind of, I think, brag that we had some significant work that we invested, as a physics community into the software realm. So that's it, and thank you for listening.
Cool, great. That's very interesting. At least to me it is. Who has questions? Everybody's quiet. I guess one thing your last comment or last page of comments made me think about is that at least in CMS, we haven't written code to want to say give me 1,000 random numbers at the same time, which looks like it's kind of the starting point for this, well, for effectively using GPUs, which is no surprise. Is that so? Have you looked at how in Atlas how to refactor your random number consumers so they don't have that problem, or maybe you wrote them right in the first place?
So yeah, I mean, I don't think it's common to have to generate 10 to the 8 or so random numbers all in one go. These are just basically test applications benchmarks where we tried to go as high up in terms of the to optimize or make most use of the hardware that we had available. I mean, you could think of one thing that we wanted to do, but we didn't have time for VCHEP was, like a particle swarm optimization type test application or something more realistic. So I guess when we see, for example, this work integrated into the FastCalloSim GPU, software, we'll have a better idea as to something that could be practical, as opposed to something that's just trying to really hammer a point home that we believe that we can achieve, performance portability with SYCL. So yeah, I mean, it's a dressed up problem, and it's not really a real problem, but it was meant to demonstrate one thing, and I think that we've done that.
Yeah, no, 10 to the 8 random numbers we probably don't need too often, but on the other hand, we often have the case where one piece of code needs a whole bunch of random numbers, thousands, but it tends to ask for them one at a time or something, and that's, I guess, just code we're going to have to fix, and have it talk to this sort of framework. So I think it's great that this sort of work's getting done, so people can start doing that. Cool. Anyone else with questions?
So actually, on that note, is it reminds me, like, we often have seen in SYCL, at least in Intel DPC++, there's some non-negligible overhead in launching kernels. So this could be like, tens to hundreds of microseconds or so. And when your kernels are small and you're not doing a whole lot, like, the launch latency is themselves really dominate the entire runtime. So that when we were doing these tests, I was also thinking, but we're not trying to compare SYCL to CUDA. We're trying to compare CUDA to CUDA, right? We're trying to say, like, this is CUDA in SYCL versus CUDA native. Whereas, yeah, But anyway, sorry, I'm rambling now.
Yeah, that makes sense. Okay, I don't see anyone else wanting to speak up. Okay, well, sorry. Thanks again, and thanks everyone for coming. We'll have more of these meetings in a couple weeks. So you should see those by the usual email channels. So thanks again, everyone, and talk to you soon.
Bye.
Bye.